Great. So we showed yesterday that e to the x has this power series representation. Okay, so what this tells you is that if you have e to any power, okay, so you wonder how your calculator knows e. Have you wondered? Do they just implement 2.71 blah 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 into your calculator? No, they don't. Calculator doesn't have e programmed into it numerically. They let me just mute you myself. They implement the power series for e. It's really cool. Not the whole thing, of course, because it's an infinite series, but they implement few terms of the power series, like maybe like 10 terms, I don't know. So if you ask your calculator, hey, what is e squared? So represent e squared as a series. All right, so we know that e to the x is equal to the sum x to the n over n factorial. So what do I do to represent e squared as a series, guys?
Just square that.
Well, you just have to replace x. This is e to the x, so e to the power of 2 is just replacing the series with 2. Two to the n over n factorial. If you expand that, beginning n with 0, we have 1, plus next term is 2, plus 2 squared over 2 factorial, plus 2 cubed over 3 factorial, plus 2 to the power of 4 over 4 factorial, and so on. Really cool. Okay, so in your calculator, I don't know how many terms of the series, it's a little bit more complicated than that, but that's how we go about it. You can actually use this series to come up with any power series that involves e to the x. For example, let's say you want to represent f of x equal e to the x squared as a power series. And I'll tell you why this is important. So all you have to do is replace x in the power series with x squared. E to the power of x squared is equal to the sum x squared to the n over n factorial. If you expand that, all you have to do is just replace, you can do it in the, well, let me actually simplify that a little bit. So that gives us x to the power of 2n. If you square x, if you raise x squared to the power of n over n factorial. And in expanded form, it is going to be 1 plus x squared plus x to the 4 over 2 factorial plus x to the 6 over 3 factorial, and so on. Why is this important? It's not just us substituting x squared into the power series. This power series can be used to do integrals that involve e to the x squared. The integral of e to the x squared, guys, first of all, this is an important integral because actually the integral of e to the negative x squared is important because e to the negative x squared is involved in the bell-shaped, the normal distribution that is studied in statistics. The graph of this function involves e to the negative x squared. And the area under that curve is probability. We need to find probabilities, so we have to integrate e to the negative x squared, okay? But e to the negative x squared cannot be integrated. There is no antiderivative for e to the negative x squared. There is no function whose derivative is e to the negative x squared. I have mentioned that before. It's one of those classic problems that doesn't have an antiderivative. So instead of integrating that, you can integrate the power series. And again, we don't need to integrate the whole series. You can just integrate, let's say, the first 4 or 5 terms, and that will be sufficient because we need a certain amount of precision. It doesn't have to be perfectly precise. It can't even be precise. So you choose a level of precision. Based on that, you go with a certain number of terms in the power series. You integrate that, and that gives you the integral of the function. Okay? Again, highly used in numerical analysis. So that's enough about e to the x squared or e to the x's power series. Again, in the next section, we're gonna see where that power series comes from. Okay, how is e to the x equal to that? We're gonna learn that in the next section. All right, so the next power series I want to talk about is the one that we saw when I began covering last section. And we've already proved it. This is the one that the 4 or 5-year-old learned actually, which says that 1 over, guys, give me a second. One over 1 minus x is equal to, let me write that in expanded form, 1 plus x squared which in summation form is n from 0 to infinity of x to the n. Okay, so we got this using both the sum of a geometric series and long division. You can prove it either way, but we've already proven this. And here, absolute value of x must be less than 1 for this thing to converge, okay? This is the interval of convergence. Absolute value of x less than 1, x being between -1 and 1 is basically the interval of convergence, meaning that this power series is valid as long as x, which is the common ratio, is between -1 and 1. For any other x, there is no way you're going to get 1 over 1 minus x equal to that series. Okay, it's just gonna make no sense when x is more than 1 or less than 1. But this is, again, this is a very, very useful power series because from this power series, we can derive power series that are in, or power series of functions that are in this form. And I am surely going to ask multiple questions on the next test and on the final that relate to this problem. Okay, so this is all about you being able to manipulate algebraically. Okay, so example, let me show you. Find a power series for this function f of x equal 1/1 plus x, let's say. Notice that I'm saying find a power series. A power series. Yes, meaning that there can be multiple power series for a function. Power series of a function. If a function can be represented as a power series, that power series is not unique, meaning that there are multiple ways that you can come up with different power series. And we'll talk about that later also. You can come up with power series with different centers, okay, centers. But we are not going to focus on centers at this moment. That's a discussion for the next section. But so here's, find a power series. All you have to do is use this power series, okay? Because this function can be written in this form. You just have to find that common ratio. Can anyone here tell me what the common ratio is for 1/1 plus x? Anyone?
Just x or negative x?
Yes, thank you, Nicholas. Yeah, negative x, and Anthony, yeah. I could write that as 1 minus, see, this power series is 1 minus x. You can replace this x with you. You know what, let me do that actually. Who cares what the variable is? It's better this way, because then you can substitute for u. Yeah, absolute value of u less than 1. So again, 1 plus x can be rewritten as 1 minus negative x. Now we identify our u. Our u here is negative x. Substitute negative x everywhere you see a u, including there. You can write it in expanded form. You can write it in series form. Let's just write it in series form. In summation form. And going from 0 to infinity, we're going to replace, again, I'm going to replace u with negative x. So negative x to the power of n. And if you want to write that, rewrite it, you could write that as negative 1 to the n, x to the n. Distribute the power to both factors of negative 1 and x. Okay, because this way we can identify the coefficients. The coefficients are represented by negative 1 to the n. Okay, can anyone tell me what is the center of this series, guys?
0.
Center is 0, yes. And Ahmed, absolutely, you can do long division for sure. Yeah, exactly. Do long division, you end up with that anyway. But I want you to be able to substitute. It's just a lot easier. Okay, this in expanded form, well, I am done right there, guys. We are done. But if you want to show this in expanded form, it's 1 minus x plus x squared minus x cubed plus x to the 4, so on. Okay, it's an alternating geometric series, power series. All right, and if you want to find the interval of convergence, we usually do that with power series. When you find a power series, you also want to indicate the interval of convergence. And again, all you have to do is replace u with negative x. Its absolute value of negative x being less than 1. Well, here absolute value of negative is just positive, so that becomes absolute value of x less than 1. Same interval of convergence. That, by the way, that reads as negative 1 to 1, excluding 1 and 1. Negative 1 and 1. That's what absolute value of x less than 1 means. Okay. Yeah. You can also find the interval of convergence by doing the limit of u sub n plus 1 over u sub n as n goes to infinity. Your u sub n is this whole thing. I promise you, it's going to give you the same solution. It'll be the same thing, but we could just all substitute. Okay? Yeah, so let's do more. That has to do with this function. Let's call this g of x 1 over 3 plus x. Okay, this is also a rational function, 1 over something plus x or something minus x. You can definitely manipulate this to rewrite it in this form. We want to rewrite it as 1 over 1 minus something. Okay, well, g of x in the denominator has that 3 instead of 1. Okay, we want this thing to be 1. Again, you could do long division, Ahmed. You definitely do that. But substitution, I want you to do it that way. I want you to be able to do that substitution. We can factor this 3 out so that this term becomes a 1. Okay, I could rewrite that as 1 over 3 times 1 plus x over 3 when you factor out. Okay, and I also want this to be a minus. I want to have a 1 minus u. Okay, so with the 1/3 in front, that fraction becomes 1 over 1 minus negative of x third. Negative of x over 3. Now we have 1 over 1 minus u. And this is some constant in front. So write that as a power series. Now we have 1/3 times the summation and goes from 0 always to infinity of, again, put that here for you. Okay. All right, and we're pretty much done. But what you want to do is rewrite this so you can identify the coefficients. You want a formula for the coefficients. So you can write that as, and I want you to do that, please. Just separate the factors. When you do that, we have a, we're going to end up with a negative 1/3 to the power of n times x to the n. pretty much. Okay, I can even separate, I could even separate the factors more here. Just separate each factor. All right, well, let's see what factors we have. We have negative. We have the 1/3. I could separate those factors. So I could rewrite it like this: -1 to the power of n over 3 to the n times x to the n. There we go. Separate the factors and raise them to the power of n. And that way you can, if you want, you can distribute this 3 or this 1/3 into the sum. Move that 1/3 into the sum. You guys know what this means. This is a sum, okay? Whatever, sum of a bunch of terms with the 1/3 in front, I can multiply that 1/3 in. When you do that, this 3 times this 3 to the n is just going to be 3 to the n plus 1. So -1 to the n over 3 to the n plus 1 times x to the n. And now we have the coefficients. The coefficients are given by this nth term. Okay, those are the coefficients. This is again the variable term, and the center is 0. So again, this is the representation. This is a representation for 1 over 3 plus x. All right, so again, the book and we both prefer that you write your series in the standard form. The standard form is this form. Okay, a sub n, the coefficients times x. If the center is 0, you can just ignore that, times x to the n. Okay, next section, we're gonna do the same thing, but with different centers. And we're gonna know what center means. But for now, yeah. A sub n, x to the n. Okay, we're not done yet. We want to find the interval of convergence. If you come up with a power series, you want to indicate when that power series is valid. Okay, this power series is not going to be true all the time. Okay, for example, if x is, say, 1, or no, 1 is no good. Say x is -3, for example. Okay, this power series is just not going to hold true. So to find the interval of convergence, you have two options. You can again do the limit of un plus 1 to u sub n, as we did in the last section. It's going to be very, very time consuming. Or you can just use the parent. This is called a parent power series. Just substitute that for u. Okay. So let u equal -x over 3 in absolute value of u less than 1. Okay, because that's what we substituted into the powers, into the parent power series. So here we get absolute value of -x over 3 less than 1, and this is an inequality that we can easily solve. Okay, again, absolute value of negative, the negative drops out. We have 1/3, you could just take that out of the absolute value, write that as absolute value of x divided by 3 less than 1, and then multiply by 3, you get absolute value of x less than 3, and that is the interval of convergence. Okay, you can also write that as the interval from -3 to 3. Okay, so again, the power series holds for those values when x is between -3 and 3. For any other x, what happens is that this power series is just going to diverge. Like imagine x is 4. Put 4 for x. Then the ratio will be 4 to the n over 3 to the n. Ratio will be 4/3 to the n. That is going to make a divergent geometric series. Not good. Okay, no way that is going to give you a finite value. Okay. Questions, guys? Yeah, Ahmed is asking, do we have to do anything? But does n always? Yes, please begin n at 0. You don't have to begin n at 0. You could begin n at 1, 2, whatever, but 0 is the standard value I start with. No, Ahmed, the power series is gonna diverge at -3 and 3. For sure, it's gonna diverge, Ahmed, because this is a geometric series. This is a geometric power series, and we know that the geometric series is going to for sure diverge when the ratio is 1 or -1. It will. Like imagine ratio is 1, then you're going to be adding 1 to itself forever. It will diverge. Same goes with -1. Okay, so you don't need to check the endpoints. This is a geometric series. Okay. Any other questions, guys? Okay. All right, let's do more. Let's just do one more quickly. So here the function, call it, let's say h of x, it's x squared over 10 plus 3x cubed. Okay, so again, we have a fraction like that. It could be, you could write that as, I could put the x squared in front and write that as 1 over, I could factor the 10 out and again, make that a 1. Okay, so let's rewrite that. I'm gonna factor the 10 out of the denominator, put the x squared in front. So now I have a 1 on the top, but 10 factored out, we get 1. And again, I want a 1 minus u, so minus here, we get 3x cubed over 10 with a negative because we factor the 10 out. Okay, there. Now we know what the common ratio is. The common ratio is -3x cubed over 10. Okay, so substitute that into the parent power series with the x squared over 10 in front. Okay, so we're going to have u to the power of n. U here is again -3x cubed over 10. Okay. And again, we're going to take care of the interval of convergence in a little bit, but once more, distribute the power of n to every factor because we want to identify the coefficients. Okay, so here we get -1 to the n, 3 to the n, in the denominator 10 to the n, times x to the 3n. Okay, you have a x cubed raised to the n, multiply the powers. All right, and that's pretty much it in terms of substitution. Distribute this again into the sum. When you multiply x squared by x to the 3n, you get x to the 3n plus 2. Okay, so we have that 3 to the n. In the bottom, 10 times 10 to the n is 10 to the n plus 1. And again, here, x to the 3n plus 2. There is your power series. Representation of x squared over 10 plus 3 to the x. Again, we want to know when this is valid. So find the interval of convergence, and again substitute the common ratio into this inequality. Okay, so we get absolute value of, again, negative 3x cubed over 10. We want that to be less than 1. Okay, ratio has to be less than 1 in absolute value for it to converge. Solve this inequality. Don't just leave it. We want to solve for x. We want to know what x is between. Okay, so again, bring things out of absolute value if you can. Negative 3 over 10's absolute value is just 3 over 10. And then we get absolute value of x cubed. I have to leave x in the absolute value, x cubed in the absolute value, because I don't know the sign of x. You want this to be less than 1, multiplied by 10^3. All right, almost done. We have a cubic x. I want to solve for x, so we take the cube root. That tells us absolute value of x has to be less than cube root of 10^3. Okay, yeah, so x has to be between that negative cube root and that positive cube root. Okay, either way, either form is fine with me. You want to express it as absolute value or interval, it's up to you.
Are the intervals always open?
Always open, yes. And again, I explained that because
Because it can't equal 1. 'Cause it
right,
won't.
yeah, this is a geometric series. It's a geometric power series. And the common ratio cannot be 1. It can't be 1. Because if it's 1, you're adding 1 to itself forever, and that gives you infinity. So it's going to diverge. Common ratio of a geometric series can't be 1 or negative 1. Okay, good. Not done yet with this section for sure. Okay. A power series has a tremendous number of applications, guys. And one of them is in Math 15. An application of power series will be in Math 15. Math 15 is called differential equations. Again, I'm sure you guys do remember what a differential equation is. A differential equation is an equation that involves the derivative of an unknown function. The derivative of an unknown function. We solved one of them again yesterday. This was the differential equation that we solved yesterday. dy dx equal to y. Okay. Remember section 7.7.5. We solved a bunch of differential equations. Yeah. And remember that to solve a differential equation, at some point, we have to integrate. Okay? But the thing is that the chance that you can find the integral of a function is almost zero. Not every function has an antiderivative. Okay, almost no function has an antiderivative. We only are able to find few antiderivatives in chapter 7. Trust me, you think like there are so many problems with integrals. There are infinitely many times functions that can't be integrated. We can't find their integral. So what we do in differential equations is that we represent y as a power series. We assume that y has like, let's say this one. It can be represented as a power series. Again, you could choose the center to be 0. And instead of finding dy dx directly, you find the derivative of the power series. We differentiate power series to find dy dx. Okay, you'll see that when you move to math 15. Okay, a power series is a function of x. It involves x. So we can differentiate it, we can integrate it. Okay. Yeah, so let's say we have a power series. Let's again choose the center to be 0. And I call the coefficients a sub n next to the n. A sub n could be anything. And we differentiate this function. This is an infinitely long polynomial. You could just take derivative term by term. All right, so this will be the derivative of, let me expand the power series. Let me write it in expanded form. So that would be a0 plus a1x plus a2x squared. It's easier to see it this way. Okay, a0, a1, a2, those are just some constant factors. They're just coefficients. Okay, there are numbers. This is, imagine this is 5. The derivative of 5 with respect to x is 0. Okay, the derivative of, let's say 10x is 10. The derivative of a1x is just a1. The derivative of a2x squared, take the derivative of x squared, it will be 2x. So we get 2a2x. We get 3a3 x squared, and so on. Very simple to take the derivative. Okay. Yeah. Now we wanna represent this derivative itself as a power series. Notice that the constant term has vanished. Okay. It's gone. The constant term is gone. So the constant of this function is now a1. You see that? It's a1. It's no longer a0. So you can begin the index of the series at 1 and starts at 0. You can start it at 0 if you want, but you have to be careful how you represent the power series. So here we have n going from 1 to infinity, a sub n. Okay, now notice that the power went in front. The power was n. Those powers are now in front. Okay, so we have n times a sub n times x to the power of, those powers diminished by 1. Okay, so this is power 1, this is power 2. Previously, this was a 3, it's a 2 now. This was a 2, it's 1. The power's gone down by 1, so you get n minus 1. Very simple. Just take the derivative of this. Bring the n down, subtract 1. But you have to be careful because n no longer begins with 0. It begins with 1. If you put by mistake 0 here, using this nth term, it's just not going to make sense because beginning this at 0, you get x to the negative 1, and that is not a power series. That can't be a term of a power series. Powers have to be positive. Okay? Yeah. So that's the derivative. The integral, same way. All right, we want to integrate. Let me write the integral here in green. Let me also write the derivative operator in green. That here too. Those are operators. So the antiderivative of a power series, of course, this is the antiderivative with respect to x. All right, so you can do the same thing. You can, if you want to see it better, you can expand. Okay, so here's the expansion for the power series a0, a1x, a2x squared, and so on. Okay, with respect to x. Now, again, you have a polynomial, infinitely long polynomial, integrate term by term. The antiderivative of a number is that number times x, so we get a0 times x. Plus, that'll be x squared divided by 2, so I can write that as a1 over 2x squared, plus that'll be x cubed over 3, so write it as a2 over 3 times x cubed, and so on. Okay? Remember, we are doing antiderivative. We are integrating. Every time you integrate a function, you need, what do we need? What do we need to add?
1 to the exponent.
Oh yeah, we did that. We did that.
Oh,
In the very end, when you find antiderivative, what do you add?
C.
Yes, the constant of integration, C. So here's our C. Notice that every power series has to have a constant. Okay, going back to the definition. Yeah, there's a power, here's a general form of power series. This A0 is the constant of the power series. Okay, so when you integrate now, you no longer here have a constant, but I have to add the constant of integration, and that becomes the constant of the power series. This in summation notation is n going from 0 to infinity, and starts at 0 because obviously here I have a 0. Okay. So what happened is that we increase the power of x by 1, or the x to the n plus 1, times the constants, times the coefficients over n plus 1. Just the power rule for antiderivatives, plus the constant of integration. Okay, and that's it. The general formula for the integral of a power series. Okay. Cool. So let's see an application. And I think we have time. Yes, we have a lot of time. Good problem. I don't know if I get to do a integral, but we want to find again, a power series representation for this function 1 over 1 minus x squared. Okay. So guys, let's talk about this problem. Is really interesting and very important. It's important because a lot of people do the unthinkable. Let's talk about the unthinkable thing to do, the wrong thing to do. So we know that the power series for 1 over 1 minus x is the sum of x to the n. Okay. This is, again, this is the parent power series. Parent power series because we can come up with other power series based on this power series by substitution. Okay. Now, someone might say that this is just the square. This is the square of that. It obviously is. This is the square of that. So why don't we just square this damn thing? Okay, yeah, we can. Why not? Let's do it. So 1 over 1 minus x squared is the same as saying 1 over 1 minus x, the whole thing squared, because 1 squared is still 1. And that is equal to the square of this infinitely long polynomial. See what I said? The square of an infinitely long polynomial. Okay. Please do not say this is equal to the sum x to the 2n. No, no, it is not. The square of a sum, that's what the square of a sum is. The square of a sum is not the sum of squares. Okay, because if I rewrite this in expanded form, we are taking 1 plus x squared plus x cubed and so on. We are squaring that again. Infinitely long polynomial. Who wants to square this thing? Can someone square this for us? Do you dare? Can you imagine foiling out an infinitely long polynomial by itself? A brain is too small. It actually makes our brain shrink. You're right. Yeah, don't waste your brain cells on it. Trust me. I mean, there are some people who see patterns and they can square things really fast, no matter what. I'm not one of them. I'm really not. We can't square that. And again, if you say this is equal to 1 plus x squared plus x to the 4 plus x to the 6, you are definitely dead wrong. Okay? We can't do that. Remember, a plus b squared is not equal a squared plus b squared. The common mistake people make, you can't distribute the power into a sum. It's totally wrong. All right, so this is very difficult to square. So this is not the good thing to do. This is not the right, I mean, I'm not saying it's a wrong thing to do. It's not a good thing to go about this, like do it this way. Okay, as a matter of fact, if someone asks to square this polynomial, what they do is they find a power series for 1/1 minus x squared, and that power series is going to be the answer. So how do we find the power series? Notice that 1/1 minus x squared. Okay, so again, here we need to find a relation between our function 1/1 minus x. This is what we are interested in. Between, 1/1 minus x squared, which is what we are interested in, and the parent function, which is 1/1 minus x, because we know the power series of 1/1 minus x. Okay, of course, this was a relation. It's not a good relation, not good. But notice that if you were to take the derivative of this, it's going to give you that, isn't it? The derivative of 1/1 minus x gives you 1/1 minus x squared. You can use the chain rule, power rule, whatever you want. But the function that we are interested in, 1/1 minus x squared, is again the ddx of 1/1 minus x. The parent function whose power series we know. All right. I mean, just think about it. This is the same as 1 minus x. You can use quotient rule or you can use power rule, but that's the same as 1 minus x to the -1. When you take the derivative of that, you get -1 minus x to the -2 times the derivative of the inside. That would be -1. Which gives you exactly that. I know the power series of that. All I got to do is take the derivative of it and we should be good. So the ddx of, and from 0 to infinity of x to the n. Okay, and we just discussed derivatives. When you take the derivative of a power series, n begins at, n is going to begin at 1. Remember, the constant of the power series is going to drop out. So n goes from 1 to infinity of n x to the n minus 1. I mean, if you put 0, if you start n at 0 with this formula, I mean, when you plug 0 in the first term is just gonna 0 out, but it's just gonna look funny because I'm gonna have a 0 minus 1. You know, I mean, things are gonna work out, but this is it. If you want to write this in expanded form, it is going to be 1 plus 2x plus, what is it? 3x squared plus 4x cubed and so on. Okay.
So
Same,
Professor,
yeah.
what would we use as the u for the interval of convergence?
The same thing. The interval of convergence is still -1 to 1, right? I'm using this power series, right? The ratio is still x, isn't it? The common ratio is still x. So absolute value of x is less than 1, right? See, look at that. The common ratio is still x. It's x to the power of whatever. So if someone is asked, this could be a good, like one of those challenge math questions on one of those like challenge math tests. If someone is asked to square this thing, and they can identify that as basically the square of the square of this function, they know the power series of that function, then they can come up with the power series of this whole thing, and it's that. Okay, so the square of that happens to be this infinitely long polynomial. Okay, but yeah, that's how you do it. Questions about this?
Yeah, Professor. So, I guess the thing that I was kind of just like thinking about right now was like, how would we know whether to like, how do I formulate this question? Like, how would we know to like take the derivative or like the integral? Like, let's say if we were given like a random, like, rational expression, like, how would we know which direction to go in?
Well, again, you have your, this is the power series. You want to come up with the power series of that. Okay, so you ask yourself, what do I do to this? What are we to do to that to get this? Because this is the power series. We know the power series of that thing. So we want to know what to do with that to get what we are interested in. And we have to take the derivative of it. Okay, this is the derivative of the parent function whose power series we know of. Okay, so here's the next example. Let's say we want to find a power series for ln of 1 minus x. All right. So again, I want to know ln of 1 minus x. Okay, I have to somehow relate that to 1 over 1 minus x. Okay, I have to rewrite the ln of 1 minus x in terms of 1 over 1 minus x, because we know the power series of that. So you ask yourself, what do I do to that to get this? What do we do, guys?
Integral?
Integral.
We do the integral. With respect to x. Now the question is that, does the integral give me right away ln of 1 minus x?
No, it gives the absolute value.
Right, it's not gonna. Because when you integrate this function, remember the shortcut, guys? The shortcut says that the antiderivative of 1 over ax plus b is equal to 1 over a ln of absolute ax plus b plus some constant. Okay. And again, by the way, here we are considering absolute value of x less than 1, the interval of convergence. But if you integrate that, the question is, do you get this? If I use this formula, the integral of that is gonna be 1 over, here a is -1. A is the coefficient of x. Okay, so the integral of that would be the negative of the ln. It's a negative of the ln. Therefore, I need to put a negative in front of this function. it's the negative of that antiderivative. You could check, find the antiderivative. You're gonna get the negative of ln of 1 minus x. So put a negative here. Okay. Yeah, and all you have to do is do the negative of the antiderivative of 1 over 1 minus x. We know the power series for that. It's again n from 0 to infinity x to the n with respect to x. You can again expand that and integrate term by term, or you can just integrate as is. Okay, so negative of you got n equal to 0 to infinity. Again, 1 over n plus 1, x to the n plus 1. I use the power rule. Okay, and don't forget that there is a plus c. Well, don't leave it like that, because we need to know what c is. Unfortunately, you have to find c, that constant of integration. Okay, to find c, all you have to do is choose a point on the curve. Okay, choose a point on the curve. And by the way, guys, I don't need absolute values here. We do not need absolute values because absolute value of x is already less than 1, meaning that this thing is already a positive. This is already a positive. Imagine x is 0.5. 1 minus 0.5 is positive. X is 0.9. 1 minus 0.9 is positive. So don't worry about absolute values. But again, we need to find c. Okay? So to find c, choose a point, or let x be any number. Take the easiest number, like 0, okay? Say x is equal to 0. Plug 0 into x, we get on the left hand ln of 1 minus 0, okay? On the right hand, we have the negative of the power series of 1 over n plus 1 times 0 to the n plus 1, where n goes from 0 to infinity, okay? Plus c. All right, so again, ln of 1 minus x is equal to this expression. I just replace x with 0. All right, 0 to any power is 0. You're adding a bunch of zeros forever. That thing is just gonna be 0. On the left hand, ln of 1 is 0. Right? ln 1 is 0. This whole thing is 0. So c has to equal 0. Okay? That takes care of that. Therefore, we have now the power series for ln of 1 minus x. It's equal to the negative of the sum of 1 over n plus 1 x to the n plus 1. Okay, plus the constant, which is just 0, and that's it.
Professor, when we plug in any x, does it have to be on the interval given?
Yes, yeah, absolutely. Yeah, make sure your x is in there. Any other x is just not gonna work, right? Like if I choose 5 for x, I get ln of 1 minus 5. ln of negative 4 is not it doesn't even exist. Yeah, it will make this power series divergent if I choose 5. So yeah, choose any number in the interval from -1 to 1, any reasonable number. Okay, I chose 0 because 0 makes this whole thing 0. It gets rid of that, and that whole thing becomes 0 also. It's just such a convenient number for this example. All right, guys. So always take the function that you're interested in and see how it relates to the parent function, the parent power series. Okay, is it the integral or is it the derivative of that? And I will see you tomorrow.
Thank you.
Thank you, Professor.
Bye, guys.